Have you ever wondered how a satellite spots one tiny ship in a huge ocean? Or how a medical AI can find a single problematic cell in a massive, high-resolution scan? Well, today, we're going to get into the super clever ways computers handle this and look at a brand new breakthrough that's really changing the game for AI vision. Let's get into it.
So just picture it. You've got an image that is just gigantic, thousands, maybe even millions of pixels wide and high. How on earth does an AI find one specific little thing, like a single car, in this enormous ocean of data? It's a massive challenge, for both computer memory and pure processing power.
The way we've usually handled this is actually a pretty smart trick. You just slice it up. Computers take that giant image and they chop it into smaller, bite-sized pieces we call tiles. Then the AI can go through and analyze each of these little squares one by one. This is called tiling, and it's absolutely key for working with today's high-res data. But as you can probably guess, this slicing solution creates its own new headache. I mean, what happens when an object, say a really long bridge or a huge building, gets cut right in half by one of those tile borders? Well, you get fragmented detections, two halves of the same thing, or you get duplicates where the tiles overlap. It's a mess. Now, to clean up that mess, we have some standard tools. One is called non-maximum suppression, or NMS. It basically just keeps the detection with the highest score and throws the rest away. A slightly smarter version, non-mask merging, or NMM, tries to stitch neighboring detections together. But here's the big problem. Both of these methods only care about one simple thing: overlap. If two pieces of the same object don't physically overlap by enough, these tools just see them as two totally separate things. They're missing the bigger picture. And this is exactly where this new algorithm, Spatial Mask Merging, or SMM, just completely changes the game. See, instead of making these tiny, isolated decisions between just two fragments at a time, SMM takes a step back. It looks at all the detected pieces at once, treating them like a big interconnected web, or a graph. This global view lets it make one single, highly optimized decision about how everything fits together. A great way to think about this is like the old methods are like looking at just two puzzle pieces and only deciding if they fit based on if their edges touch. SMM, on the other hand, is like a detective stepping back from the table, looking at all the pieces scattered around, and using a whole bunch of different clues to see the complete picture before they start snapping things together. So how does this smart engine actually pull this off? Well, it really comes down to three core ideas that make it not just smarter, but way faster too. So let's pop the hood and take a look. Okay, first up, speed. You see, comparing every single fragment to every other fragment would be painfully slow. So to get around that, SMM uses something called R-tree indexing. Just think of it like a super efficient GPS map for all the fragments. When SMM looks at one piece, this map lets it instantly find all of its potential neighbors without having to search the entire image. This is a huge speed up. It's what makes the whole process scalable and efficient instead of getting bogged down.
Second, let's talk about its intelligence. SMM doesn't just ask a simple yes or no question, like do these two pieces overlap? No, it creates connections. These are the edges in the graph we mentioned. And it gives each connection a score, or a weight, based on multiple clues. Things like how close are their boundaries? How much do they overlap? And maybe most importantly, how confident is the AI about each piece? By combining all these clues, it builds a much richer, smarter understanding of whether two fragments really belong together.
And third, there's this brilliant safeguard built right in. SMM has something called an anti-chaining rule. This stops a really common mistake where, say, object A gets merged with B and B gets merged with C, but A and C are actually parts of two totally different things. SMM has a rule that says, hey, wait a minute, for a final group to be formed, every member has to be compatible with every other member. No more cases of mistaken identity through a middleman. It's a fantastic little logic check. And to bring this all together, how do you find the perfect balance for all these different factors, like the weights for the connections or the distance rules? Well, SMM uses a really clever process called Bayesian optimization. You can think of it like an automatic supertuner. It intelligently experiments with different settings on its own to find the absolute perfect combination, squeezing out every last bit of performance.
All right, so the theory sounds incredible, right? But how does SMM actually do when you put it to the test in a real-world competition? Let's take a look at the results.
The big headline number is this one. SMM delivered a nearly 7% boost in precision over the very next best method out there. That means it is significantly better at making the right merges and avoiding the wrong ones. In this field, that is a massive leap forward. And this table really shows you the magic behind its efficiency. The old methods, they grow quadratically. That's the O of n squared, you see. In plain English, if you double the number of objects, the processing time quadruples. It gets slow fast. But look at SMM. It scales so much more gracefully. That n log n means that even as you throw thousands of objects at it in a really crowded scene, it stays efficient. It doesn't grind to a halt. Now let's look at something called panoptic quality. This is a great metric because it measures two things at once. Did the AI recognize the object correctly, and did it trace its shape accurately? And as you can see from the chart, SMM is the clear winner here too. This proves it's not just better at recognizing objects, but it's also better at perfectly reconstructing their full shape from all those scattered fragments. So yeah, a 7% jump in precision and a better quality score. That's awesome for researchers. But what does this actually mean for the real world? Why does this smarter way of seeing things really matter? So let's just quickly recap the big wins here. SMM gives you globally consistent results. It stops those sneaky chained errors. It's super scalable because of that R-tree indexing we talked about. It's built from the ground up to solve the tiling problem. And maybe best of all, you can use it with pretty much any AI model. You can just plug it in at the end of the process and instantly get better results. And the applications for this are just huge. I mean, think about medical imaging, where you absolutely have to piece together a perfect view of an organ or a tumor. Or autonomous driving, where a car needs to build a single clear picture of a pedestrian from 5 different camera angles at once. Even things like industrial inspection, looking for tiny flaws on a massive airplane wing. This kind of tech is a foundational improvement for all of them. So I'll just leave you with this thought. Every single day, we are mapping and scanning our world in more and more detail. And as we do that, algorithms like SMM, the ones that can actually step back and see the entire picture, not just the tiny pieces, they're going to become absolutely essential. What new things are we going to discover when our AI can finally see both the forest and the trees?